Welcome back. This is week 7 of inverse methods in heat transfer. In the last video, you saw how to show that the maximum likelihood estimate using a probabilistic technique gives us the same result as minimizing the least square. So this was the connection between the current approach that we are using, which is a probabilistic approach, and the function approach that we used earlier. Remember, in our probabilistic approach, all we are trying to do is to build a probabilistic model of how y, the output, depends on x, the input, and also whatever parameters we have, w0, w1, etc. Okay. And then we try to maximize the probability of this happening, which is what is called MLE, or maximum likelihood estimate. And we try to find out the parameters that we can vary in order to accomplish this. So this is what we saw in the last video. Now, in this video, what we are going to do is to go 2 steps further. First step is what is known as maximum a posteriori. And the next step is what is called a full Bayesian estimate. So I will do this in some detail, and once again, you will see an interesting correspondence with what we had done earlier in our function approach. And the Bayesian approach, I'll just give you a brief outline of, because it's in some sense too complicated for this class. In advanced courses, you can do it. It is too complicated for this class to do theoretically. We will, however, see how to make Bayesian estimates computationally in the coming videos within this week itself. So let's get into this topic. So remember, all of what we are going to discuss depends on what's known as Bayes' theorem. We saw that earlier in the last week. Bayes' theorem simply says that P of y given x is P of x given y, Py, divided by P of x. And of course, as we saw in the examples, P of x itself is given by marginalizing over the joint distribution for all possible values of y. Okay, so you basically understand that in case we have a case like cancer versus no cancer, then we want to know, do I have cancer given this test? Then I sum up over all possibilities. That will I get a positive with cancer? Will I get a positive without cancer, etc., etc. You sum up over all possible y's, and that's how you get P of x. Now, as it turns out, and as we will see when we come to the Bayesian estimate, this quantity can often be really hard to compute. This is usually something which I called the prior. This is called the likelihood. And this is called the posterior. Now, of course, I can switch x and y also, and that's the form in which we are going to do it right now. Okay. Now, instead of using x and y, which is what I did in the previous video as well, I'm going to use something that's a little bit clearer. So I'm going to say data and parameters. So typically data is called y, and parameters we had called w. So we are going to see it this way. Actually, data itself was a combination of x and y. But let's now come to this thing of how do we estimate the parameters given the data. Now, what was MLE? I'm going to rewrite MLE in this form. MLE said, what is the parameter that maximizes the likelihood of observing this data? So we saw this last time as well. So the question really was, find out probability of the data given the parameters and maximize this probability, or maximize, we usually did log of probability. Okay? And this is what gave us the least square estimate again. Now, but this is not the right question, as you can see. So this is what was MLE, right? This is not the right question, because actually what we are asking is the other question. What are the best or most probable parameters given the data? Okay. Okay, so if you see this, the dependency is flipped. We say, okay, I am given the parameters. How can I generate, or which is the set of parameters that generates this data in the most probable sense? Whereas here we are asking for a different probability distribution, probability of parameters given the data. So this, like I said, is called the likelihood, and this is what is called the posterior. Why? So let's write it this way: probability of param given data is probability of data given parameter multiplied by probability of parameter divided by probability of data. This, of course, is Bayesian. Okay. Now let's write this in our old XY notation. So I'm going to write this as probability of W given the data. The data was basically a combination of both X and Y, is probability of data, which is what we call likelihood, X comma Y given W. Now, you might remember earlier that in the previous video, I had just written this as P of Y given X comma W or comma A comma B. I'm writing it in this way because this makes the dependence a little bit clearer. There is some formal difference between these two expressions, but we are going to ignore it because that will get too much into probability theory and why we can use it in this form. But right now, casually, you can think about this. I am given the data, or I am given the parameters, and then I can find out the probability of a given data set. Here, I am given the data set and I want to find out what is the best parameter that fits it. Okay. So this multiplied by probability of W divided by probability of observing the data. Now we can therefore write that probability of W given the data is proportional to, we wrote this earlier too, probability of X comma Y W multiplied by PW, where we have noticed the fact that this is independent of the parameters. Now, if you find out that W that maximizes log of this probability or just the probability, this is called the maximum a posteriori. That is, in fact, I should put this in small, maximum a posteriori or a posteriori estimate of W. Other words, this is called MAP. Okay. MAP standing for maximum a posteriori estimate of W. Okay, so this is called. Whereas if you maximize this, you get MLE. Okay, maximum likelihood estimate. This gives you MAP. Now, what is the difference between these two? The difference between these two is this quantity, which is the prior. We saw in the COVID example that the prior significantly affects what probability you get here. So in case, I'm going to again say this a little bit casually, in case we have a uniform prior, okay, so this would mean that P of W is equally likely for all W. Okay, so this is not quite possible because we have W has an infinite range, but let's assume that that was the case. In that case, you will simply get P of W comma XY is proportional to P of XY, and there is no other dependence on W. This will give you MLE is the same as map. Okay. So physically, what we mean is this. MLE and map are the same if we have no information about W. So suppose you are estimating the thermal conductivity of a material. Suppose you are estimating something else about that material, or you have an MRI scan and you're trying to estimate the image. And if you have no clue about what the parameters you are trying to find out are, or you have no clue about their range, then you can simply do a least square. Okay, so this means least squares is the best estimate. Both map as well as MLE. But in case we have a prior, that is, we have some idea. So let me give you an idea of a prior. Okay, so let us say we are dealing with two parameters, A and B, or yeah, let's just take two parameters, A and B, and we know that these parameters are Gaussians, or we know that they have means around 0 and they have some sigma. Okay, so let's say I have these two parameters and we know that these are random variables. So for example, let us say we have conductivity and we know that the K is one of the parameters we are estimating, and it is, let's say we know it is made of steel and it is going to vary between, let's say, 50 watt per meter Kelvin to 55. Okay. If we have some such estimate, then you know that you can sort of fit. Okay, I again request you to go back to the examples we did in the previous week. For example, for the pipe, etc. So all these cases have some mean and some standard deviation. So the special case that I'm taking here is, let's say we have two parameters where the mean is 0 and the standard deviation is, instead of calling it sigma, let me call it beta. Okay. So if we have this, then there is a prior. Okay, so then there is a prior. And this prior is going to affect this a posteriori PDF. So we are going to call this first the prior probability distribution function. So the prior probability distribution function for A, for example, let's say probability distribution function of A, PDF of A, is 1 by square root 2 pi beta square e to the power minus A square divided by 2 beta square. So this is the probability distribution function of A, because now A is a normal variable with mean 0 and standard deviation beta, or variance beta square. So similarly, PDF of B is also in fact exactly the same thing, because I have kept the same parameters for it. We can change this and make it different parameters too. That's not a big deal. In fact, we have asked one such question within the exercise problems. Okay. So PDF of B is exponential minus B square by 2 beta square. All right. So now we take log of probability of W given X, Y is log of the probability of Y or XY given W plus log of probability of W. Why am I taking log? I am doing exactly the same thing that we did in the last video. What I want to do is to maximize the posterior probability. Instead of that, I maximize log posterior probability. As you can see, this log splits nicely also into addition. Now, if you remember, we had actually already calculated this. This calculation was sigma of 1 by square root 2 pi sigma square plus, so that should be log of sigma of log of 1 by square root 2 pi sigma square. We can simplify this, but I am skipping that step. And plus you saw sigma of log of the probabilities of e power minus s square, we call it epsilon square, by 2 sigma I square. And for now, we will take the simple case where we assume all sigmas are the same for the new term. The new term being due to this. So if you remember, there are two terms here, PDF of A and PDF of B. So I will just say log of PDF of A plus log of the PDF of B. Why is that? Because the probability of W, we are assuming that A and B are independent parameters. All these are assumptions which need not be true. This depends on the fact that probability of W is probability of A multiplied by probability of B. And of course, that would mean that log of P W is log of PA plus log of P of B. Okay. Okay. So these terms, let me write that out. Just these terms then come to plus, notice e to the power minus b square by 2 beta square. So I'll first put the constant term 2 times log 1 by square root 2 pi beta square, that handles the constant, plus the next term, which was minus a square by 2 beta square minus b square by 2 beta square. Okay. So when I want to maximize this, these terms, the terms that I'm circling right now, these don't matter because these are constant terms. So this term doesn't matter. This term doesn't matter. The only terms that matter are these three. So we will maximize minus sigma of y hat square or y minus y hat square by 2 sigma square minus a square minus b square by 2 beta square. Okay. So you can now write this as minimize j. So I'm removing the minus. I'll put a 1 by 2 sigma of yi minus y hat I square plus, I have removed the minus, remember, sigma of wi square, where w0 is, let's say, a and w1 is b, by 2 or lambda by 2, where lambda is equal to sigma square by beta square. Basically, if you multiply this equation by sigma square fully, you get this. Now, if you notice, this term is exactly what we had for what we call ridge regression or regularization. Remember, we called this L2 regularization. It was also Tikhonov. Okay, so we actually recovered the fact that Tikhonov regularization is the same as adding a prior. Okay. Now you can do more sophisticated things to get the kind of stuff that we got for Liebenberg, Marquardt, etc. But I'm not going to do that. I mean, you will basically have to show that there are covariances, etc., etc. So I'm not getting into that. But the interesting thing here is that we naturally recovered the idea of regularization through a maximum a posteriori. So we can call this J map, if you wish, is J MLE plus this term, which is J prior. Now, what does this prior mean? Okay, this prior basically says that depending on this beta square and the relative certainty of the data we have collected and the relative certainty of the prior that we have. What does the prior say? In this case, we are saying I don't want either A or B to be far away from 0. Okay. So the more and more beta you give, you more and more leeway you give for A and B to be, let's say you have something of this sort. It says, okay, within reasonable noise, 95% of the data can be in a large range. So as you increase beta, you can see that lambda decreases. That is the weightage of the prior decreases. But as you decrease beta, the importance of the prior increases. So another way to see it is, if this is the MLE distribution. Okay, so the MLE distribution or the data distribution is, remember, this is with sigma. This tells you what would be the pure prediction for a particular parameter, let's say A, if the only thing it wants to do is to fit the original data. Okay. So let's say the original data is like this, and all you want to do is to fit some best fit line. Okay. So once you want to fit this best fit line, you will account for all the errors here, which are sigmas, and you will give a distribution. You say, okay, my parameter lies within a particular range, but the most likely value of the parameter is the one that fits this least square thing best. This is called a point estimate. Okay, I told you this earlier. Point estimate means we are giving only one value for this W1 or W0 or both as we estimate them. Now, apart from this, we have another piece of information, which is the prior. The prior says, okay, you might get some value of W1 here, which is the slope, but I have a prior requirement that the slope should not lie out of a particular range, or the more and more you want to push it out of this range. Let's say you are estimating the thermal conductivity of a material and it is steel, and your best fit actually happens to say that thermal conductivity has to be very, very low. It has to be 1. Now, this is a bad idea because you know the material is steel and it has very low manufacturing probability that thermal conductivity is going to be extremely low. So we want to incorporate this prior information. So what we do is, this prior information affects the likelihood, and put together it gives you a posterior, which is somewhat of a balance between the two. Okay. So you can say that likelihood plus prior leads to posterior. If the likelihood is strong, then the posterior distribution will strongly bias towards the likelihood. If the prior is strong, the posterior will strongly bias towards the prior. What does that mean in our sigma and beta terms? So let's say the likelihood is strong, means sigma is very low. Sigma is very low means I have very low errors in what is happening here. My thermocouples are really accurate. Then If sigma is low, lambda becomes low. If lambda becomes low, this term dominates, and you would like to minimize this strongly, and therefore your posterior will strongly bias towards the likelihood. Similarly, if beta is low, then this term becomes very high. This term becomes very high. Your map will strongly bias towards the prior. Okay. So what we have right now is, in this video, we have shown theoretically that regularization is the same as incorporating some prior information about a material or about the parameters via regularization. Okay, so the regularization that we did earlier could be rederived. We also saw that the posterior is affected both by the prior as well as the least square estimate that sits there. Now, in the next few videos, this might all be theoretical, and I have a couple of small theoretical questions within the exercises. But in the coming videos, we will actually see how to make this computationally operational. Okay, so this can't be calculated theoretically for most cases. We will come and see how to do this computationally using a chain of techniques or using a set of techniques called Markov chain Monte Carlo techniques, or generally Monte Carlo techniques. So I'll see you in the next video. Thank you.